In today's lesson, we are mastering the fundamentals of deductive proof. You will learn how to use formal logical arguments and algebraic manipulation to prove that a mathematical statement is always true. This is a vital skill for the IB Diploma, as it forms the bedrock of mathematical reasoning. You will find proof questions appearing across all papers in the Analysis and Approaches syllabus, often carrying significant marks for your ability to show clear, logical steps. By the end of this session, you will be able to distinguish between equations and identities and use the left-hand side to right-hand side method to construct rigorous proofs. Today, we are discussing the concept of deductive proof. In the IB curriculum, a deductive proof is not about guessing or looking for patterns. That is, inductive reasoning. Instead, deduction provides absolute certainty. We use established facts and clear algebraic steps to show that a statement must be true under all defined conditions. Before we start proving, we must understand the notation. An equality using the standard equals sign typically refers to an equation that is true only for specific values of a variable. For example, 2x equals 10 is only true when x equals 5. An identity, denoted by the triple bar symbol, is much stronger. It means the expressions on both sides are mathematically identical for every possible value the variable can take. In your exams, when you see the identity symbol, you are being asked to prove that one side is simply a different way of writing the other. Visually, an identity means these two shapes are the same size regardless of the value of x. The standard layout for a simple algebraic proof in IB mathematics is the left-hand side to right-hand side approach, or LHS to RHS. To perform this correctly, follow these steps. First, isolate the expression on the left. Use techniques like expanding brackets, factoring, or finding common denominators to change its form. Continue until the expression is identical to the right-hand side. A common mistake is treating an identity like an equation by moving terms from one side to the other. In a formal proof, you must work on one side only to demonstrate that it transforms into the other. Let's look at an example. Let's start with a numerical example to see the logic in action. We want to show that 1/4 plus 1/12 equals 1/3. We begin by stating the left-hand side. To add these fractions, we need a common denominator. Since 12 is a multiple of 4, we can convert 1/4 into 3/12. Now we add the numerators. 3 plus 1 gives us 4, so we have 4/12. Finally, we simplify the fraction by dividing both the numerator and the denominator by 4. This matches the right-hand side perfectly. Notice how we worked vertically, showing every logical step until the conclusion was inevitable. Now, let's apply the same logic to variables. This is where deductive proof becomes powerful, as it allows us to prove a relationship for infinitely many numbers at once. Show that 1 over m plus 1 plus 1 over m squared plus m is identical to 1 over m. We begin with the left-hand side. Our first insight is to factorize the second denominator. Notice that m squared plus m can be written as m times the quantity m plus 1. To add these, we need a common denominator, which is m times m plus 1. We multiply the first fraction by m over m. Now we combine them. The numerator becomes m plus 1. We can now cancel the common factor of m plus 1 from the top and bottom, provided m is not -1. By showing these steps, we have proven the identity. Let's look at a proof involving expansion. Again, we start strictly with the left-hand side. The first logical step is to expand the squared binomial. Remember that squaring a bracket means multiplying it by itself. Using the distributive property, often called FOIL, we expand the brackets. X times x is x squared. Then we have -3 times and another -3 times. And finally, -3 times -3 is +9. We combine the like terms, -3 times and -3 times, to get -6 times. Finally, we add the constants 9 and 5. This exactly matches our right-hand side. We have successfully proven the identity through clear algebraic transformation. If you are ever unsure during an exam, you can substitute a simple value like x equals 0 into both sides. Since both equal 14, it supports our proof. though remember that substitution itself is a check, not a formal proof. Let's tackle an authentic IB-style question. We are asked to prove that the difference between the squares of two consecutive odd or even integers, represented here by n plus 1 and n minus 1, is always 4 times n. We start with the left-hand side. Method 1 is direct expansion. We expand both squared brackets carefully. Now, we distribute the negative sign through the second set of parentheses. This is a common place for errors, so be careful. Notice the n squared terms cancel out, and the positive and negative ones also cancel out, which equals the right-hand side. Alternatively, you could recognize this as a difference of two squares, in the form a squared minus b squared. Substituting n plus 1 for a and n minus 1 for b, the left-hand side becomes, this simplifies to 2 multiplied by 2n, which is 4n. Both methods are mathematically sound, but the second is often faster in a timed exam. We conclude with LHS equals RHS, therefore the identity is proven. The most frequent error is moving terms across the equal sign. Remember, in a formal proof, you must not balance the sides. You are transforming one expression into another, not solving for a variable. Many students write x plus y squared as x squared plus y squared. This misses the middle term. Always expand carefully. X plus y times x plus y gives x squared plus 2xy plus y squared. When subtracting a polynomial, like we did in the exam question, students often forget to change the signs of every term inside the bracket. This leading error can invalidate the entire proof. IB examiners look for a logical flow. If you skip steps or don't clearly state LHS and RHS, you may lose communication marks even if your algebra is correct. Always finish with a concluding statement like LHS equals RHS. In IB exams, the phrase "show that" means the answer is already given to you. The marks are awarded for the quality and clarity of your derivation, not the final result. Even if you make a small algebraic error, you can still earn most of the marks if your structure is correct. Always start with LHS equals and work vertically. This signals to the examiner that you understand the formal requirements of a proof. Before you start expanding everything, look at the right-hand side. If the right-hand side is in a factored form, it is often more efficient to factorize the left-hand side rather than expanding it and then having to factorize it back later. When stating the initial problem, use the triple bar identity symbol. For all the intermediate steps where you are simplifying, use the standard equals sign. This demonstrates a sophisticated understanding of mathematical notation. Ensure your final line is exactly the same as the right-hand side provided in the question. If the question asks for a specific form, you must reach that exact form to get the final accuracy mark. It's time to test your understanding. Please pause the video and attempt these 3 questions. The easy question asks you to show that 2x plus 1 squared minus 4x is identical to 4x squared plus 1. For the medium challenge, prove that 2 over k minus 1 minus 2 over k plus 1 is identical to 4 over k squared minus 1, where k is not equal to plus or minus 1. And the hard question, show that n squared plus 1 squared minus n squared minus 1 squared is identical to 2n squared. Take your time with the algebraic steps. When you are ready, press play to see the full solutions. For the easy question, we expanded the squared bracket, which generated a middle term of 4x. This canceled perfectly with the minus 4x, leaving us with the right-hand side. In the medium question, we found a common denominator of k minus 1 times k plus 1. When we expanded the numerator, the two k terms canceled, and the constants added to 4. For the hard question, expanding the quartic expressions allowed the n to the power of 4 and the constants to cancel, leaving 4n squared. By expanding the RHS separately, we confirmed they are identical. First, remember that a deductive proof uses logical steps and algebraic manipulation to show a statement is always true. Second, understand the difference in notation An identity is true for all values, whereas an equation is only true for specific values. Third, the left-hand side to right-hand side method requires you to work on only one side of the identity at a time. Fourth, to maximize your marks, always show every algebraic step clearly, such as expanding or factorizing. Finally, always conclude your proof by explicitly stating that the left-hand side equals the right-hand side.